Welcome everybody tonight to the forum. For you that don't know me, I'm Zara Champion. So I run these forums. I work very closely with Mia, and I also, as my other job, look after Biotech New Zealand. So I'm the executive director. So again, I connect those companies that I have in my membership with the students that are in the Bioscience Enterprise, and also again for these forums. So tonight I'd like to welcome you, Will Barker, Dr. Will Barker. So Will has, I'm really looking forward to hearing where Will is now with his company. Will has spent 7 or 8 years in LanzaTech before creating really Mint, and he was also the CEO of NZ Bio for 3 years as well. So Will, I'm really looking forward to hearing where you've gone. We were just saying it's about 2 years to date that Will presented to a similar crowd here, and I think there were 2 of you or 3 of you that were in the lab squirreling away, and now you're 14 in the lab, so that's pretty exciting in terms of your growth there. So yeah, I'm going to hand it over to Will.
Brilliant. Thanks ever so much, Zara. I've actually 2 years, I think, to the day, and I was a little bit concerned about what I was going to talk to you about today. And then I realized that I actually presented to the Bioscience, or not me, myself, but we'd presented to the Bioscience Enterprise students last week a very similar story. So what I'm going to do is try and put a little bit more color into it to at least keep it a little bit fresh for the younger part of the audience. Apologies to the older part of the audience. So I actually spent most of today, a bit of background about myself, as Zara indicated. I spent about 7 or 8 years at LanzaTech, and now founded a new clean tech company, which kind of I guess pigeonholes me as a clean tech sort, somebody who is at least on paper passionate about the environment, passionate about creating technologies that mitigate the damage that we're creating, that we're causing on this planet. I find that quite a challenging tag. I find that quite a challenging. I certainly don't feel that I'm that sort of person. I spent most of today at a conference, an investment conference, really interesting one actually, one of the better conferences I've been to. Blackbird Venture Capital, Australian venture capital firm coming to New Zealand. Really good conference. They're going to run it annually. Recommend going. But anyway, they opened it with a poet, a slam poet, who and I don't know what slam poetry is. But slam poetry, turns out, is this kind of forceful message, but also delivered in quite a forceful way. And this slam poet, and I thought, my goodness, I can't think of anything worse. Anyway, this slam poet was a Samoan girl who was she was 17, and she was dressed in kind of this. For the older parts of the audience, the young ones, Rick Mail from The Young Ones, you know, the Mao cap and the denim jacket with the badges, that sort of get up at this investor conference. But her message was extremely powerful. She's basically grown up in a world today where there is a climate emergency, and she is looking at this from a Polynesian perspective, a Samoan perspective, where the Samoan culture and a lot of the Pacific cultures are all about storytelling from prehistory. So they've got this story that kind of goes back millions and millions of years, or hundreds and hundreds of years. And what they're seeing on TV all the time about this climate emergency, everybody's complaining about all the CO2 we're putting in the atmosphere. Everybody's complaining about the cars being driven, about all the flights that we're taking. But what it really means is the first people that get affected by this is the Pacific. The Pacific is basically fucked. The Pacific will disappear first. They are the first ones that are going to feel the true impact of this. And essentially, the history of these proud people is going to go. And the message that she gave was so powerful and made me, really quite uncomfortable in the way that I'm a tech developer. I've been working in clean tech for over 10 years, and find it very difficult to actually tell a message that is positive about clean tech. Whereas she comes, she's a 17-year-old girl, not that interested in clean tech, but has this really very, very strong message. So I now feel slightly more inspired that I'm doing something positive for the world. We're in clean tech, we're looking to develop technologies that are actually having a positive difference, reducing the use of resources, reducing the impact of on the environment. So that's, I guess, a brief introduction in why clean tech is important. Where did we start with Mint? We, as Zara indicated, I was with LanzaTech for many, many years, 7, 8 years. I think most of the bioscience enterprise students learn about LanzaTech, and as a case study, it probably hasn't changed a great deal since it was written about 8 years ago. But it is a great case study in a startup business taking a test tube theory and creating a technology that actually does have a positive impact on the world and mitigates some potential climate damage. So what they do is they take a steel mill waste gas, carbon monoxide containing gas, they convert it through to ethanol using a microorganism. So steel mill waste gas contains carbon monoxide contains carbon, and it has energy in it. So these microbes, they eat the carbon monoxide, they chew it up, they metabolize it, turn it into ethanol, and they spit it out as a metabolite. The principle behind LanzaTech is that the ethanol can be collected and sold as a biofuel. I joined the company when it was literally a test tube. I at the time was a patent attorney and working on their patent portfolio. At the time, it made sense for me to step out of the firm that I was working for and work in-house with LanzaTech, as they had this global aspiration. At the time, I had no illusions that it was going to be a success story. They had literally a test tube. They had some results that just looked horrendous. They had zero chance of scaling this technology in my mind, but I thought it would be a fun ride for a couple of years. Over time, they took it from test tube, they took it to pilot scale, they took it to demonstration scale, and they took it to what's now commercial scale. They have commercial facilities open in China and looking to deploy this technology throughout the world. So from pretty simple, humble beginnings, they went on this wild ride, 10-year journey, and very, very successful. My journey there kind of ended as they chose to take their technology, take the all of the IP out of New Zealand and start developing it in the US. They moved to Chicago. I took the opportunity to step out of LanzaTech and start looking for a new technology to essentially do exactly the same with. Take an early stage technology and start growing it into something fantastic. My skills are pretty limited when it comes to, there's very, very few jobs that I could do other than commercialized technologies. I'm a patent attorney. I worked most of my LanzaTech career was doing capital raising, was doing partnerships, that sort of thing. So I can only work in startups. So really looking for a technology that makes sense was almost my sole option. One of the challenges that we found at LanzaTech, one of the principles that we really found very, very difficult to commercialize and get people's heads around was when you've got a waste to value opportunity, your waste stream always has value. Your waste stream always has a carbon content and has a calorific content. And because it's got carbon and calorific content, all of a sudden people think it's valuable. People think they can start charging you for it. In steel mills, they're pissing out carbon monoxide, and yet when you say you can do something valuable with it, they want to start charging you with it. So it's got a value. And when you're talking about ethanol or small 2, 3, 4 carbon molecules that can be used in biofuels, can be used in bioplastics, they've also got a value. But typically, because they're such small molecules, they've typically got quite a low value. And one of the challenges that we found at LanzaTech was the differential between those two values. The delta there is actually quite small. And in a clean tech play, an infrastructural type clean tech play where you're trying to build a plant to do this business, typically those plants are upwards of $50 million. You've got this small differential between your feedstock and your product, trying to squeeze in a capex of $50 million. The economics get quite challenging quite quickly. So when I stepped out of LanzaTech, I really wanted to stay in clean tech for obvious reasons, and identified if we're going to do this, I really want to maximize the value of the differential, the delta between the input feedstock, waste stream, and the product. So we started looking at precious metals. We identified opportunity around essentially taking precious metals from very, very low concentration feedstocks and recovering them using some form of clean technology. We identify printed circuit boards as a fairly serious waste stream. We identify catalytic converters as a waste stream that contains a lot of value. We identify mine tailings or even mined ores that contain precious metals, and using some fairly catastrophically or environmentally catastrophic chemicals like cyanide to recover those metals. So what we see is there's clearly an opportunity for a clean and scalable precious metal recovery process. Can we develop that with using a clean technology? Well, where we started looking kind of, when you're developing a technology like this, you're really looking for a low-hanging fruit opportunity. What we identified as a low-hanging fruit opportunity was printed circuit boards. Now, electronic waste is everybody knows, massive problem. There's 50 million tons of electronic waste thrown away every year. The vast majority of that ends up in landfill. And of course, these things contain all sorts of nasties. It rains, those nasties dissolve, those nasties ends up in the watercourse. Part of that waste has been well recognised that there's significant value in these waste materials, printed circuit boards in particular. They're kind of the noxious end of your electronic waste. They contain all the nasties, but they also contain some interesting precious metals like gold, like palladium, and some of these things are sent offshore, shipped over to developing nations where they're use rudimentary recovery techniques to capture the metals they're in. Some of it ends up going to these kind of mega smelters. But the interesting point here is that the electronic waste, the electronic waste that's sitting in your pockets right now, or the future electronic waste that's sitting in your pockets right now, equates to about 500 tons of gold being thrown away every year. So a massive opportunity to recover value, and a massive opportunity to mitigate some serious environmental and humanitarian harm caused by the destruction of these items. So what we developed, and cutting a relatively short story shorter, is we developed a clean, low-cost process for recovering precious metal for waste. This is an investor slide, so it contains all the investor highlights, all the things that they like to see. It's as a process, we effectively, it's a drop-in process. So we work with local recyclers who are already recovering waste. We take their waste, we basically size reduce it, then we put it into our plant, we dissolve off the metals, and we use our magic microbes to produce pure metals. The principles behind that is that it's scalable. Now, the big challenge for recycling is in order to get the value out of the materials that you're recycling, you have to send that recyclable material offshore. You have to ship it typically from New Zealand all the way up to the northern hemisphere before any value can be captured. This happens to countries all over the world, and you've got vast volumes of electronic waste ending up in these remote locations and literally shipping junk around the world to these central locations. So what we've developed is a scalable solution that means that you can capture the value at the point of collection. So build a plant where the waste is recovered, where the waste is actually collected, and recover the value there. In order to do that, you have to have a very low-cost plant, otherwise nobody's ever going to build it. In order to recover the value from any waste stream, it has to be low OPEX, or a low operating cost process. If you're going to build it in a city, it needs to be small footprint. If you need investment, you need to have some IP around it, and it needs to be compatible with the existing infrastructure. And that's exactly what we've developed. We've developed this process, we've developed this microbial process that essentially takes microorganisms that can go into a solution that contains very, very low concentrations of metal. These microorganisms go into those solutions that contain low concentrations of metal. They selectively suck up the precious metals, the metals of interest, the gold and palladium. And because these microorganisms have got mass, you take them out again and recover the metal. Now, typically a feedstock stream that's got these precious metals in, it's going to be in the low parts per million concentration of metals. Perhaps more challengingly, you think about printed circuit boards, if you dissolve all of your metals off and to get a solution of gold, you've essentially got a toxic cocktail of all these different metals, with gold being one of the lowest concentrations in there. What these microbes do is they go into the solution. They selectively suck up the metals of interest, particularly the gold and palladium, and because they got mass, you take them out again. And what we've got an ability to do is go from these very, very low concentration, part per million concentrations, up to a concentration of roughly 10% of their body weight. So you've got this very, very cheap, low cost, renewable method of concentrating 4 or 5 orders of magnitude, very selectively concentrating gold and palladium. Very quick, it's renewable, specific, works in the context of all these different metals. But the most exciting thing about this is this is entirely renewable. You grow these things on sugar, and they're constantly able to replenish and recover precious metals. That's what we developed in the lab. We started 4-ish years ago. At the stage, it was all proof of concept stuff. It's literally test tube stuff. Unlike university developed technologies, a private technology like this is developed slightly differently. We're kind of making it up as we go along. I am a chemist, but a long time out of the lab, so all of the kind of early work. Found out fairly quickly that you do forget chemistry skills. You can go from being a relatively safe chemist 12 years ago to being an incredibly dangerous chemist once you start sitting at a desk all day. So got in this guy here, Ollie Crush, who's much closer to university than I was. And he essentially came in. I identified the principles that we wanted to commercialize, and got him in on a contract and said, look, see what you can do. Screen some bugs, screen some chemistries, and see if you can develop this process to recover precious metals from the microorganisms. He did exactly that. And did it in very, very short order, but also during that process he clearly had an aptitude to commercialization. It's literally straight out of university, but very, very well read and very, very knowledgeable about the various different aspects of commercialization. So really had a very good understanding of IP, had a very good understanding of what a cash raise would look like, and an ability to develop the materials needed to go out and raise that capital. So I brought him in as a co-founder, and together we went out back in 2017 on the basis of the test tube scale results, went out and raised that capital to start a company. 2018 was basically the promise that we had made to those initial seed investors was we'd take the test tube and scale it up, prove it works at a certain scale. In our case, that we considered 20 kg scale to be appropriate. That's basically taking 20 kgs of waste material, printed circuit board material, and extracting the gold and palladium from that material. And that might be producing maybe 2-4 grams of gold at a time. So interesting amounts of gold, visible amounts of gold that can actually take to an investor and say, look what we've got here. We did exactly that. It all worked very well, and it enabled us to secure the IP. write some patents, got the team together, and essentially grew as a company throughout 2018. As we kind of get closer to the market, having a piloted process, we now identify kind of the stepping stone that we need to achieve before we get into market is showing that this process can be done at a scale that makes sense to the market. Okay, it's no good showing that the investors are happy with a pilot plant, but the market is not going to be happy until they see scale, see something that's where you're showing exactly real world volumes. So we identified then we'd need to raise a big chunk of money, went out, raised $5.2 million, and that's enabled us to now build what we're calling a pre-commercial demonstration of the technology. That's ton scale, so that's taking a ton of waste material and recovering the metals from there. We raised that money at the back end of 2018. We've been building that plant throughout 2019 and we're now operating. I'll show you a little bit more about that in a little bit. But for us, kind of the onward journey from there, next step for us, secure some commercial partnerships in jurisdictions of interest and then start looking to deploy plants in these scalable plants in the jurisdictions so we can recover the value from the waste that's being collected. So, and for me, this is the most exciting part. I'm a technologist, I'm a tech developer, so I get most excited about doing chemistry at scale, doing things that nobody's ever done before. But what does that really look like at scale? You can kind of imagine, everybody knows what test tube chemistry looks like. People can imagine what a pilot plant looks like, but what does it start looking like at commercial scale? Well, first thing we had to go and get ourselves a warehouse, and I think Jason's around. Jason Herbert, who's an ex-Bioscience Enterprise student, a relatively recent ex-Bioscience Enterprise student. He was tasked with go and find us a site where this will work. And interesting, you would think warehouses are 10 a penny. Warehouses that are going to let you do a brand new chemical process in are not 10 a penny. He down selected from the 1,000 that are on the market down to one site that was able to do exactly what we wanted and would tentatively allow us to do that. We spent, I don't know, 3 or 4 months working with this guy, this old landlord guy who had this place out in Swanson in West Auckland. And he was clearly quite nervous about letting us this technology to a technology company developing this brand new technology, and over time we comforted him, and we essentially essentially agreed to pay him more than he wanted. We did literally everything we could to convince him that he'd give us this site, and it got to the day that we signed the agreement, and he turned around and said, "I've changed my mind." So that was a good learning for Jason, and a good learning for us that you always need a backup. And this is our backup. So an empty shell. It's about a 400 square meter warehouse down in South Auckland. And then you've got to build the plant. Now this guy here, this is Nick Milletta, who I worked with Nick for a long time at LanzaTech. And Nick was instrumental in designing things at LanzaTech, and then he was also instrumental in building pilot plants and demonstration plants in strange places with strange materials. So Nick has a unique set of skills, almost again like mine, completely untransferable to the real world, but is very, very good at kind of startup stuff. Nick had a far worse time at LanzaTech than me. He spent most of his time running these plants in far-flung areas of the world, so he really should have known better than join another startup and do the journey again. But anyway, he agreed to do it, and he genuinely gets a kick out of doing these things. But Nick sat down. He understands the process. He draws it out on a piece of paper. He goes through the process of transferring it into engineering drawings, goes through the process of transferring it to a commercial product, essentially, what the tanks look like, where all the pipes go and all that stuff. And then once he's done that, I'm a cheapskate, so I said, okay, now rather than hiring an engineering firm to do it, I tell him that he has to build it, and he's done exactly that. I think he's probably about to resign. He has absolutely had enough of me, but he has managed to build a fairly impressive looking plant. Now these vessels, these vessels here are about 6,000 litres. So this plant, I always like to say, it has a look and a feel of a microbrewery. When I show this plant with hydrogen peroxide and filter presses in containment, people kind of start losing the thread of it being a microbrewery. But anyway, I still like to call it a microbrewery. So a 6,000 litre vessel, able to take a ton of material, able to extract 200 to 400 grams of gold at a time. So we put a ton of material in, and we get a lot of value out of the other end. So that's where we're at now. We've literally started recovering gold out of the end of this week. This week? Where is it? Wednesday? Yeah, this week. Just a little bit more detail on what the process looked like. We take printed circuit boards, I don't even know what that word says, but we reduce the size of it. We have a hammer mill. This is one of the most dangerous items I think I've ever seen. It's a bought it from China. It's got basically a row of hammers that swing around at an absolutely insane speed and smash whatever's in its way into a very fine powder. It's typically got a lid on it, so we don't have somebody with their fingers over it. But it is a very, very frightening piece of kit, and we end up with this fine powder. This fine powder is the printed circuit boards. Now, printed circuit boards are about 20%, about 20, maybe 30% metals. The rest of it is your plastics, your ceramics, your epoxies, your glass fibers, that sort of thing. So what we need to do in the first instance is remove the less interesting metals from that matrix, from that kind of inert matrix. So our first step is what we call a base metal leach. We rely on the reactivity series of metals. So all metals have different reactivities. Aluminium is very reactive, gold's very unreactive, and all the other metals sit in between. And copper kind of sits somewhere in the middle. So what we do is we dissolve all the metals down to copper. And leave on the plastic, on the matrix, we leave the gold and the palladium and a bunch of other metals. Then we go into the next stage, which is the precious metal leach, and then we're looking to dissolve the last of the metals that are less reactive than copper, and that requires an acid and an oxidant. And that goes through the process, dissolve off those metals, and then you've got the metals floating around this solution, ripe for bioabsorption. So the bioabsorption piece, we take microorganisms. We've got a whole suite of microorganisms, but this is a well-studied and well-defined microorganism. And what these things do, they've got pockets amongst of basically cavities in them, and they've got these active transport mechanisms to draw interesting precious metals out of solution. They also get totally covered in precious metals. They essentially, stuffing it in pockets, wrapping it in jackets, and they get covered in gold. They also reduce that gold from gold 3 in solution, the oxidized form of gold, up to gold 1, and then to solid gold or pure gold. Pure gold doesn't really exist in a microbial form. This is microbes covered in pure gold. It's actually gold nanoparticles. So gold nanoparticle absorbs light, which gives it this fantastic purple color. And this is now about 10% gold. So this is microorganisms coated in gold. One of the challenges, or probably the main challenge from a technology perspective, is the precious metal leach. In order to dissolve the metals, in order to dissolve in particular precious metals, you need an acid and an oxidant. And if there's two things that microbes really, really hate, It's acids and really hate oxidants. So kind of the key technological development that we've done is developing a leach system that is consistent with that ability to use microbes. They don't survive, but they don't, explode. So microbes are the hero of the story. You just grow them, again, microbrewery type analogy. You just grow them in a bioreactor. Super easy to grow. They grow at they have a doubling time of about 90 minutes, and then we harvest them, and we've got this stinky paste which is suitable for microbial collection. You basically just harvest them through centrifugation. Once you've done your bioabsorption step, again at larger scale, you've got this absolute filth, but this is essentially this purple nanoparticle covered gold microorganisms. Again, the hero of the stories collected all the gold, and so moving on to recovery. So we just set fire to them, and once burnt away, we are literally left with a nugget of gold. So not just a low cost and kind of simple way of recovering these metals, but also extremely clean. These things, these microorganisms, they literally disappear into the atmosphere and leave us with this fantastic gold nugget. From a business perspective, why on earth would anybody think this is a good idea? Why on earth would they want to work with us, particularly if they're able to recover value from others? At the moment, there's the kind of the status quo, if you like, is the people recovering this waste. They're sending this stuff off to these mega smelters around the world. The challenge that they face with these mega smelters, firstly, they need to export the material. They need to they need a license to export the material. So they need to get an export license, a Basel Convention export license, which is no mean feat. Then they need to ship it. That's got insurance, and obviously takes time to send to the smelters. Once it gets to the smelters assay it. So it lands on the dock, if you like, or it lands in the car park of the smelter. And the smelter is in control of telling the recycler how much value is in this printed circuit board. So there's a complete power imbalance, and recyclers, all being crooks themselves, have zero faith in the smelters, zero trust in the smelters. Then once the smelters have done it, there's very, very few smelters, very non-competitive, monopolistic environment. It's also a low recovery process. So they're essentially sending back about 40% of the gross value of the material. Our low-cost process enables us to provide much more value to the recyclers, but also able to do it in much faster. Rather than the 6 months it takes for the smelters to pay out, we're able to put the material through our process, receive and put it through our process in weeks. It's easier, it's faster, it's transparent, it's cleaner. And you can't see this on the bottom, but it's one of my favourite things to say. It's got quadruple bottom line advantages. Now that's investor speak for, there used to be a thing called triple bottom line advantages. So if it's more profitable, it's better for the environment and better for the industry. Then there's triple bottom line advantages. The new thing is quadruple bottom line advantages, and I'm not even sure what it means, but it does sound very good. Market size, total addressable market. This again, investor speak, but what we're essentially trying to do is capture the market, enable this local recovery of the value in markets of interest. The main markets are the obvious markets. They've got the US. They really know the value. They've got a very sophisticated market where they've known the value of the printed circuit boards for a long, long time. So they've got this sophisticated collection market. Europe is another good market, strongly driven by mandates because Europe is obsessed with regulation, and China, of course, being a massive market because they are extremely populous. So the opportunity for us is to deploy plants into these different jurisdictions, right now focusing on Europe in particular, and Australia, which is quite a unique market as well. So massive market, If we even vaguely get anywhere close to those numbers, then I'll buy beers are on me. The opportunity for us is not just printed circuit boards. You've always, again, got to have this massive vision of where you're taking the company. But the tonnages of printed circuit boards are significant. They already exist, and they're obviously, it's a challenged market. So we think very, very addressable. But again, once you're talking to investors, particularly overseas investors, it's always got to be, well, what's beyond that? What's the vision beyond printed circuit boards? What's the vision beyond being $1 billion company? Oh, why do you need a vision beyond that? 10 million will do me. 1 million will do me. Anyway, we've got this story around the addressable market. Printed circuit boards is a growing. Printed circuit boards. This is the collected circuit boards. More become collectible if you're able to recover the value. But more interesting markets are catalytic converters. The number of catalytic converters on the road is expanding, and the amount of catalysts in those converters is increasing annually. Mine tailings represents a good one, and then a future market, just for really blowing people's socks off, is the $3 billion ton per annum mining market. So that's just about me, and I have no idea how long I've taken. I always go on way too much, so I apologise for that. But I am very, very happy to take any questions if you have them. I've noticed it says 1 hour and 9 minutes. I surely haven't spoken for that long. I hope, if I have, I'm very, very sorry if I've just wasted an hour of your life.
So thank you, Will. I've just got one question. In terms of, you mentioned cell phones, is that something you would look at?
Yep. So cell phones. So part of the one of the interesting dynamics of the market is that over time everything miniaturizes. Computers even 10 years ago used to be all desktops. Now they're all laptops, tablets. Or you can do with your cell phone what you could do with a mega computer 10 years ago. So printed circuit boards are getting much smaller, but now they are in just about every device that you're carrying around. So you've got this miniaturization that is offset by the proliferation of cell phones, by the fact that everybody carries around far more eventual waste. Printed circuit boards do contain, cell phones do contain that waste material, or that future waste printed circuit board material, but that's actually really, really high concentration valuable metals, because as you miniaturize, you need to use increased concentrations of the core active ingredients, if you like, the interesting ingredients, because you need better conductivity, you need better electron flow, you need to be able to remove your heat from these things more easily. So the miniaturization is being offset by the proliferation.
Thank you.
I think one of the really attractive things about this technology is the distributed aspects. And it seems like that's perhaps the next step for you, is to distribute. How do you intend to...
Sure. So that's essentially what commercial success looks like for us, is building distributed plants. So we're currently going through the process of identifying, again, the low-hanging fruit environments, the low-hanging fruit jurisdictions where we can deploy that first, second, third plant. So we're already talking to potential customers in a bunch of jurisdictions and identifying where's best. And we will look, once we identify those customers, once we get a commitment from those customers that they will supply us with printed circuit boards, we'll be able to raise capital to build those first plants. And I've got a view that we'll be able to do that a handful of times before it becomes quite unwieldy for us as a company to own multiple plants worldwide. But once you've kind of proven that at the scale that we're looking to prove it at, and commercialize it in that manner, then you start looking for kind of those bigger, broader, strategic type licensing plays, where from the waste aggregators, the global waste aggregators, the Veolias of the world, the waste managements of the world. So yeah, in short answer, that's exactly what we're doing right now.
I read a paper last year, I can't remember which one it was, but they were using solution and create these whole filament wires. Are you familiar with that?
Yes, I am, and if you can do that, then that's absolutely it's almost a better way of doing what we're doing. We're doing it crudely, and we're doing it cheaply, and we're doing it in a way that can make sense on an economic basis. If we were able to immobilize the microbes that we use, and this is work that we will do at some stage, then it does make sense to do that, because you literally dip it into the solution and then you take it out again, and then you can recover the microbes. Unfortunately, the only way we have right now of recovering the metals off those microbes is setting fire to them, and of course producing biofilms takes time. So it is work in progress, but that's a fantastic way of doing things. Particularly, and beyond precious metals as well, it becomes a technique for removing these microbes. Go in and they literally suck up every last vestige, every last atom of down to very, very low concentrations. So we're talking, we've got five parts per million that we're able to bioabsorb, and then you're going down to sub-part per million parts. So you're able to cleanse water of other metals. So potentially using it as a bioremediation as well. Again, it's been well documented that that's possible, but being able to do it in a way that makes sense and commercially makes sense is massive.
Simple's good.
Simple's good, definitely, especially when you're paying the bills, definitely, and that's what investors want. So.
Who are your competitors and how are you different?
So the main competitors, or the competitors that exist in the market today for printed circuit boards are the smelters, and the smelters are well, they're actually copper smelters. So they've grown up in the 50s and 60s of these massively billion-dollar plants to recover copper. And as this opportunity, as printed circuit boards have become an increasing problem, they've retrofitted to recover the valuable metals from themselves. But the market has grown in a way that's not particularly sustainable and is not particularly fair to the customers. So and it comes down to scale. Smelters are able to offer this scale that enables them to do it, but you need that mega scale to be even vaguely profitable. And those things run on fine margins at the best of time. So what we're doing is offering a completely different perspective. Is you capture this value at low cost in the location of collection. And so far, the conversations that we've had is, please help me. Yeah.
Can we hear a little bit about the microorganisms involved? They're presumably sulfate-reducing bacteria?
They actually...
Which is stuff that's been known about for quite a period of time, so I'm sort of wondering, I'm interested in
what we're doing that's new
from and what the IP position is with respect to what your biological systems
sure.
You're using are.
Yep. So these guys, yep, you're absolutely right. And actually, when we identify these microorganisms, we're taking them out of we're taking it out of the literature. It's well-known stuff. And even if we weren't taking it out of the literature, these things have been they've been absorbing metals for 1 billion years, probably more than 1 billion years. So from a novelty perspective, which is important for writing a patent, being able to absorb metals, there's nothing novel about it. But what we've done is we're exploiting that bioabsorption, if you like. We're exploiting that bioabsorption to selectively bioabsorb the metals of interest, which they do naturally anyway. And then because we're taking them out of solution and because we're purifying them, you've got this method of effectively increasing the concentration by several orders of magnitudes, selectively concentrating the metals of interest. So the IP is not around the microbes, it's around that method of concentrating.
But don't these microorganisms also accumulate silver and other?
Some of them do.
So we're, in terms of just competing with the cyanide process, I'm struggling to see where your competitive advantage is.
Yeah, you can't use cyanide many places these days. Cyanide's banned in just about every country other than New Zealand, Australia, South Africa, but on those sorts of commercial scales. But we don't look to competing with cyanide. You couldn't build a cyanide plant to recover precious metals from printed circuit boards, for example. So what we're offering is an ability to we don't use the microbes to dissolve the metals. The metals are dissolved using using chemistry. We're simply using microbes to go in there, and we're using them as effectively a low-cost sponge. They go in there, they do their sponging up of the interesting metals. The microbes that we've selected, they don't biosorb silver. They only biosorb the really interesting metals, the gold and palladium. So very, very selective. But equally, very, very interested in microorganisms that have other properties for other metals. So able to go into a solution and biosorb, for example, cobalt. If you're able to do that, then you're able to fix a problem that is going to be horrendous for the world in 10 years' time when all these batteries come to the end of their life. But look, there's nothing particularly clever about these microbes, nothing particularly clever about what we're doing. It's just a well-balanced combination of chemistry and biology, and the IP is as much of a protection mechanism as it is a story around investment.
Got one last question. Oh.
Well, I love the talk. Another question about the microbes and the biology. Can you genetically engineer these so that their active transport is increased?
Can I?
Can they? Can we?
Potentially, yeah. I mean, we're just doing it extremely crudely, and as I just said, extremely as simple as we can. But potentially, yeah, absolutely, they can be manipulated to do better stuff. The metals that we're most interested in at the moment, they do that kind of just because they've always been doing it. But cobalt, you know, there's other microbes that have particular affinity towards cobalt. If you're able to increase the bioabsorption or the mechanisms around cobalt, then yeah, I'll be very interested. That'd be great. That'd be fantastic. I might even pay.
Well, I think we'll leave it there in terms of questions. One last is when will your company be leaving New Zealand? Are you going to follow in the same footsteps, or are you very much a New Zealand-based company?
We are absolutely a New Zealand-based, and I guess one of the, again, it was a learning from LanzaTech, is LanzaTech was always destined to head offshore. As a biofuels play, they had to really. The feedstock they need is steel mills, of which there was one tiny one in New Zealand, and the products they're producing are competing with the oil industry. So from a commercialization play, the chances of them kind of being successful from New Zealand was always very, very slim. So again, when we were founding this company, we were looking at opportunities to low capex, low opex, maximising the delta between inputs outputs, but also looking for opportunities that can be scaled from New Zealand. Again, not a great deal of our plants will be based in New Zealand, but we can certainly deploy our plants from New Zealand because they're much simpler, they're much lower cost, and very, very easy to deploy. So I certainly hope not. I'm here for the long run.
Yeah. Thank you, Will. Everyone like to put their hands together.